Bismillahirrahmanirrahim. Assalamu alaikum warahmatullahi wabarakatuh. In today's video, we're going to discuss the topic of inductor design for power electronic circuits. Before going into any requirements or calculations or anything, we have to revisit our previous knowledge about inductors. Inductors can be circuit elements like this or a schematic like this. And we have studied in this course about various types of transformers and inductors. We have studied about isolation transformer, ferrite core transformer, silicon steel laminated core transformer, and many things. The problem and the question comes to your mind is, why do we have to specify all of these things: core size, area gain, number of turns? We just want to specify main specifications like the power rating, maximum current, some things like this. And the answer to this question is that in real life implementations of power electronic circuits, we face unexpected phenomena related to electromagnetism. To get deep into this, we just want to visit a transformer. If we apply an AC source here between these terminals, we have a time-varying magnetic field cutting this coil, having a flux linkage, inducing a time-varying voltage or an AC voltage step down because of the Turner's ratio. But if we want to convert DC to DC, stepped up or step down or whatever you want to do, how to do this here, how to use this transformer to step up or step down DC voltage. You only know that this transformer only can deal with time-varying source or a source producing a time-varying magnetic field like the DC source. The problem here is you want to change this voltage or get pulses from this DC source to this coil to, like, you want to trick this transformer to play on it like you're producing an AC, but it is not an AC, it is a unidirectional changing magnitude voltage, and you induce on the other side, on the secondary, another voltage, and you try to rectify it and filter it to get it to your load. So you try to step up or step down according to the Turner's ratio. We are not designing transformers specifically, we are designing an inductor. So we are more interested into boost converters. In boost converter, we have a MOSFET. This MOSFET is to open and close this circuit repeatedly to provide some changing voltage to this coil to amplify this voltage to this circuitry. And this is a rectifying diode and capacitor like a filter. We are not interested into details about this boost converter. We just want to use this example to understand more what is happening here. What is the problem now? What is the problem? In this circuit, we don't use this type of transformer. Usually, many people use this type of transformer called the ferrite core inductor. And some use this like an isolation transformer of ferrite core also in flyback converter. This is a flyback and this is boost converter. From our previous knowledge from electromagnetic fields 1, we know that materials go linearly with the magnetic field. With increasing magnetic field, we are increasing the flux density, and if we open circuit this coil, it goes back to zero. But in ferrite materials, with higher permeabilities, there are some phenomena with some different behavior with changing magnetic field. We have the domains of the material, ferromagnetic material, going in some direction. If we applied external magnetic field, it goes like this in one direction with the direction of magnetic field. And then if we open circuit this coil, what happens is they do not come back to this form. They do not come to a random point. The problem here is, if we are going like this, increasing the magnetic field strength, increasing the flux density, or what we call later on in machines residual flux in this core, we are approaching a point of saturation. So if we detach this source, we're not going back to this point. We are going back to a point of residual flux like this, like you are going from this point to this to this. And if you give another pulse to the MOSFET, you go like this, like this, like this. So you're more likely to saturate your inductor core early on. And what happens if you saturate this coil? What happens? What happens is that you cannot store any energy. This inductor is not inductive anymore. And the problem with having that is you are losing your inductance. Losing your inductance is losing a part and a main part of your circuit and a main part of your impedance. Losing a main part of your impedance, you know that I is equal to V over omega L or XL. Going down with this L is going up with this I. Going up with this I can damage your whole circuitry. This current is passing here, passing here, passing here. You can damage the whole circuitry of the boost converter. And this is an advantage for flyback converter having an isolation transformer. You can just damage this MOSFET in the primary circuit. To avoid this situation and avoid having a residual flux and a redundant coil, you have to study this curve carefully. And the difference between this curve and this curve is this curve for AC. You go like this, go to saturation, go in the negative, go down, then go in the negative portion, and in the other direction, and go across this loop, around this loop, over and over and over again, having what we call hysteresis losses, which are the area under the curve. Uh, it, this is proportional to b power n multiplied by the frequency of this AC current. In DC, we are just into this curve, or we can add this small curve of retentivity to be more precise. But why this is not AC or any direction, if you want to view this and get more insights, we can go to LT-Spice. These are two different boost converters, or I think they are the same, just different PWM to the gate of the MOSFET. One of them is having a square wave, and one is having a triangular wave. If we review with them, these are the pulses at the gate of the MOSFET. One is triangular, one is square wave. These are the output voltages at the capacitor, output voltage to the load here. And these are the currents passing through the inductor. They are not sinusoidal. They are not even close to sinusoidal. They are not behaving in two directions, as you can see. They are fluctuating between 2 points or two rough values. They are behaving like a saw, like some sort of a triangular wave. So the RMS of this current, you can see it. The RMS of this current is not like sinusoidal. You cannot calculate this RMS by taking I maximum over root 2. It is not even logical. In power electronics, we deal with square wave, triangular wave, McDonald wave, and many sorts of waves. So this simulation on LT-Spice can be useful to validate my work. We have 120 volts. We have here about 190 volts. This is a boost converter. In the input, we had 20 volts. Here, we have a very large number compared to our input. So going back to our problem, and here we want to design this inductor to achieve what we want. We want an inductor with 0.4 millihenry of inductance with maximum current of 5.5 ampere, and we have validated that we will use I maximum, not I RMS, as we can calculate this RMS values. We don't even know what is the type of the wave for various applications. We don't know. We don't have any indication of the application we would use this inductor on. So we want to have B maximum, as we have seen here, to avoid saturation, to be 0.25 Tesla. We want our copper losses to be maximum 1 watt at a temperature of 25 degrees Celsius. 25 is the room temperature. We use this room temperature because the copper wire is having a changing resistivity with the temperature, so we are targeting the resistivity at a certain operating temperature. To understand this copper losses, we should go to this book, and as we can see in DC mode of this inductor, after steady state, this becomes a short circuit with a series parasitic resistance of this wire, and this parasitic resistance may have voltage drop. This voltage drop increases with value of the resistance, resulting in a higher power losses into heat. We want to make this losses a maximum 1 watt. Then we have KU. It's called a fill factor. Fill factor is that we have the core is something like this. When we are going around with this winding, this wire cannot fill all the gaps. As you can see, we did, in this core, he didn't fill all of this space. You can always have a tight hand or a tight grip around this winding to fill every single point of this space. This area is called the window area. It's called the window area. So you can look into it like a window, and you cannot fill it to 100%. So there are some limitations and some tolerance you have in your winding, and in this case you call this tolerance KU, the fill factor or utilization factor, as it indicates your utilization of this window. So I think we have covered many things so far, and we have to start with the calculations. First things up, we need to specify the core size. So to specify the core size, we have some givens. With these givens, we want to go to the criteria of the problem. The criteria of the problem is that we use the KG method. KG is that we are picking up this core according to the geometry constant of this core. We have this information. With this information, we can calculate the KG from the rules here in the book. KG is calculated from this formula. this for specification. But if we want to calculate from our givens, we use this formula and this formula. We try to calculate this number. We have resistivity is given at as the temperature, room temperature is 1.724 by 10 to the power of negative 6 ohm for each centimeter. And we just substitute in this equation, having the resistance. To calculate the resistance, you have 1 watt maximum power losses and current of 5.5 ampere. We use the maximum here because we do not have any information about the RMS. Get the resistance, the maximum resistance. We are targeting a smaller value of 33 milli ohm at maximum for this copper losses. You go to this formula, substitute for 0.4 millihenry, 5.5 ampere, resistivity as we have mentioned, a quarter of Tesla, 33 milli ohm, and 0.5 for the Ku, and you get eventually this value. You're looking for a core with a higher geometric constant than 0.809. So to select a core, you are going to this document and look for a number larger than this number, and you will find this. This is reasonably higher, so you choose the EE50. EE50 with some parameters and specifications. So you have chosen this EE core, and you want to calculate the air gap length. What is air gap length? You have cores like this having air gap. But why we are interested into air gaps? Reluctance is equal to the mean core length over the permeability multiplied by the cross-sectional area of this core. And in air, mu is equal to mu node. And in ferrite, mu r is a large number, like 1,000 or more. And in this case, you have a larger permeability, resulting in a lower reluctance. And if you calculate the overall reluctance of this magnetic circuit, you'll find that the overall reluctance is approximately the reluctance of the air gap. So you try to lower this reluctance as much as possible by lowering this air gap. So to calculate this air gap, we go back to the book and go to this rule and substitute in this equation. We have to we have mu node is 4 pi by 10 to the power of negative 7. We have the inductance, we have I maximum, we have B maximum, we have this constant. But we don't know what AC is. AC is a cross-sectional area of the core. We have it chosen. It is 2.26. So you go to substitute in this equation. A great disclaimer here. So you have to use these units. Otherwise, you will ruin your results. So be careful with the units and the constants. Be aware of everything. You are going with these calculations. Substitute and get your numbers, and you will get an air gap of 1.0764 by 10 to the power of negative 3 meters. As you can see, this is in meters. Then, after this, you want to get the number of turns. So to get the number of turns, you go to the rule, calculating the number of turns. You have L, you have I maximum, you have V maximum, you have AC. Substitute in this equation, and you will get 38.9, approximately 39 or 40 turns. Then we want to evaluate the wire size. Wire size AWG is called the American wire gauge, like an international indication or something. I don't know if it is a standard or what. Then we go to look for anything related to wires. Wire size, we have AW. It's called the bare copper area. Bare copper area, you calculate it from this formula. Look for a lower number, lower than this number. We have the number of turns, about 40. We have Ku is 0.5. We don't know what this is. This is WA. We can look for it here. And this is a winding area, 1.78. Substitute in this equation or this formula and get 0.02282. Look for a lower value in the American wire gauge, and you would find you must multiply it like this by 10 to the power of 3, and you will get 20. This after multiplying by 1,000 is like 22 and 82. It is here 20.002, and you select AWG14. This is AWG14 with a resistance of 82.8 micro ohm per centimeter. And we are done with this core. It's called EE core. We are required to calculate for EE and EC. We will repeat the same process once again for EC. Here we have kg is also 0.809 because there is no difference. It is not related to the core. It is independent on these names. It is only dependent on these parameters. So after having this number, we are going to look here in EC, look for a larger value. It is 0.914 EC52. Choosing EC52 with a cross-sectional area of 1.8 centimeters squared, we are looking for the air gap length. Go back to the book to this equation, substitute using a cross-sectional area of 1.8, getting the air gap length to be 1.35 millimeter. We want to determine the number of turns. To calculate the number of turns, we have to substitute in this equation, having the number to be 48, or we can say approximately 49 or 50. To evaluate the wire size, we also substitute once again in this inequality. With KU, we have it 0.5, and WA is 2.12. And get our values, check on this value, multiply it by 1000, get 21.63. Looking for a smaller value, just smaller. No, you cannot go to 2 from 21. You go for a slight smaller value, the most suitable one. So you have here AWG14 20.02 with the same resistance. It is the same wire once again. So we have specified everything. We have specified everything, every single point required in the problem. And now we have to come to a conclusion. We have to comment on this and have a point of view about this work and these results. So I think there are slight differences between EE and EC. In EE, as you can see here, we're using a square cross section. In EC, we are using a circular cross section with circular winding. We have here square winding. So the differences that we have more turns here. We have 40 here. We have 50. This change is we can calculate the resistances of each design. In this design, EE is having a parameter called the mean length per turn, the average length of the winding, as you can have a wire here, loop here, loop here, loop here, and you want to get them the average. You want to get an average value for the length of each loop, so you can calculate the overall average length of the used wire in this designs. So you take this mean core length, mean length per turn, 10 centimeters. Here 7.5 centimeters. Having the same resistances, for here we have resistance and the same resistance, you can multiply the mean length per turn by 40 here and by 50. By this number, get the resistance of the overall resistance of this wire and this wire multiplied by 5.5 squared, and see which one is bigger, and you will get that EE has more power losses than EC by 6%. So the difference is now that you have a smaller air gap here by a good value. A good value, you can say about 20, between 20 and 30%, resulting in a lower overall reluctance of the circuit of the EE than the EC, as we have mentioned in this part. So point one in the conclusion, that you have a lower reluctance for the EE core, but you have more copper losses by 6% in EE than EC. Another problem that you can have some problems with the tightness of the winding or around round area or circular areas, and they have mentioned here in this book. I don't know if it was what they meant about this chapter. I don't know, but we can consider it. Another consideration here is we have the air gap length, we have the copper losses, and we have differences. Yeah, we have slight differences in the shape we choose according to the application. I don't know if there is another problem or another factor I have left, but overall they are nearly the same. I can choose for a sharp criteria. I can have a certain criterion that I can say choose EC over EE, vice versa. I don't know, but I think there are some applications you can need EE over EC or EC over EE. I don't know. In a matter of fact, what's a certain criterion to have a rough decision? I'm going to choose EC. No, I'm going to choose EE. I don't know, but they are nearly the same. You have some points you can say about resistances, about number of turns, the length of the wire, the cost, the air gap length, the overall reluctance. I don't know, but I think this is the topic we are into discussing today, and I think that's it. That's it for today's video, and see you next time.